recording. Hi, we're recording now. We'll do pseudorandom generators today. Recall where we were last time and see efficient, like more realistic PRG construction. Oh, that's not what I wanted to do. I switched off a video, sorry about that. No, I wanted to just switch it to a document camera, yes. Okay, it's very not in focus, but okay, let's see. Okay, so okay. So what was the construction we had last time? Right, we just iteratively applied PRG to itself. So let's say let G be PRG from that maps n bits to and here let's say that it outputs n minus c n plus c bits for c greater or equal to 1, right? Like last time we just said that it outputs 1 bit more than the input, but of course if it natively outputs c more bits, that's even better. And let's do it for all n. Okay, so basically it's a asymptotic construction that somehow given if it gets 100 bits, it outputs 100 and c. If it gets 101 bits, then it outputs 101 and c, right? And the iterative construction of G prime that would given n bits, it would give n plus polynomial for any poly p was that G prime of x was basically G of G of x. So I iteratively applied G to the output of G. So I start with n bits. This guy gives me n plus c. This guy gives me n plus 2c, etc., etc. So how many of these do I need to take? I need to take I equal p of n divided by c instant, repeat number of G calls, right? And so claim that we argued last time was that if G is a PRG, then G prime is a PRG for any poly P. And the intuition was that no, sorry. Actually, we have done this only for the special case of I equal 2, where we just run G on G outputs. That's what we did last time. But so let's do it more generally here. And basically, it's by induction. If let G of I of x be G applied to application of G, right, in a loop I times. Then claim if GI is a PRG then so is gi plus 1. Because gi plus 1 can be expressed as I take a g to the output of gi of x. And so basically you generalize the previous proof, right? Because now you have the following. Here is gi, which takes an x and creates some output. And then you feed that output into a single instance of g. And that's so. So you start with x from random n bits at random, right? This is what x is, and then this output. Well, that's this output z is distributed. This is like gi plus 1 on x for x uniform, right? So again, un random over n-bit strings. So that's a distribution, uniform n-bit strings. And we wanted to show that this is indistinguishable from just a distribution of well, how long the outputs of this gi plus 1 are. Every time I add c bits, so I guess this is n plus c times I plus 1. That's the last distribution. What is the intermediary distribution? The intermediary distribution is this one. I feed this guy x prime taken from uniform what n plus ci bits, and this is my z. So you can see, I mean, each of these have this number of bits, okay? And these two are indistinguishable by inductive hypotheses that GI is a PRG. Because, again, it's the same reduction argument. If anyone tells this z's from these c's, then you would build a reduction that distinguishes this type of values from these type of values. How? The reduction takes an input and feeds g of this input, this type of z, to the attacker. If whatever the attacker says, the reduction outputs. And if y's come from gi x for x uniform, then these look indistinguishable from, let's call this distribution d0, and let's call this distribution d1. Then z look like taken from what is z? Is it g of y? Y is gi of x. So this is gi plan. So this is this distribution, right? They look like from d0. If on the other hand, y is a random n plus ci bit, then z looks like from d1, right? Because it's d1 is take a random n plus ci bit and apply g to it. So this value will hit this distribution if y looks like an output of gi, and it would hit this distribution if y is a random string. So this shows that so this is an argument for this statement, that if this reduction would attack gi as a PRG, right? Because by feeding the g of y input to a. So if a, notice is the difference between d0 and d1. So okay, so this is this guy a distinguishes the 0 from the 1, supposedly, right? And R breaks the security of the PRG G prime. Let's call this distribution, let's call this distribution D2, okay? And that these two are indistinguishable. Well, that's by PRG property of G, right? Because that's explicit right here, right? Like this is just, this distribution is take G on a random string. This distribution is take a purely uniform string of the size that is like the outputs of G on inputs of this size. And right? Okay, so this is a generalization of the argument we saw last time. Any questions on this picture? Okay, on this whiteboard here.
I have a question.
Mm-hmm.
So this proves that G to the power of Y is a PRG for every Y, for every I, right? But not necessarily, we are not necessarily done. Like, how do I explain this? I depends on N, correct?
Yes. Mm-hmm.
So it's not a PRG to with expansion N plus Pn. You are fixing I, and so you are fixing an N, which you can call like uppercase N. And then that's a PRG.
Well, I'm arguing that that if I restrict this construction to any number of these rounds, okay, so I can think of this inner guy as G to the 1, this is G to the 2, and so forth. Then I will, whatever my final polynomial is, my final number of I, which depends on N and C, yeah, whatever it is, I will be arguing a security by essentially a sequence of these arguments made however many I times needed.
Right, but my point is that I is fixed. Like, it's a PRG because when N goes to infinity, you can't distinguish, right?
No, N doesn't, no, you cannot talk about like infinities. Yes.
No, I mean like
this argument will break down if N is even like exponential time.
No, I mean like N is the security parameter for the PRG, correct?
Yes, it's this initial seed here, yes.
Right, so I can't depend on the security parameter because the security parameter is not fixed.
Oh, I see. No, I can depend on the security parameter. There's nothing wrong saying that, whatever my security parameter is, I'm going to, so let's say you fix the security parameter at 100, and let's say you want to encrypt, 100 million items. At this point, I is 1,000,000. If your security parameter was 200 and you wanted to still encrypt just 1,000,000 bits, then this would be, half that.
Yes? Okay, so your PRG is defined for a specific security parameter.
Look,
that's what's confusing.
I'm saying that it works for no matter what the polynomial is.
Just that in the induction, it seems like N is independent of I. In the induction, because in the induction you are using a PRG on the variable N, right?
Wait.
I think that in
the
caps there's
the inductive thing is I, right? So that's my parameter in the induction. I. The input outputs of these algorithms, I mean, it's n always, and the output size is n plus I plus 1c, right? So that's how gi plus 1 looks. It has n bit inputs and it has this much bits outputs. And I can define it for any I. In the end, what I need is that I is some, I want to make this work for any I that is some polynomial function of n. And I don't see a problem. This argument would work because, excuse me, basically I would run this argument polynomially many times. Yes, this argument argues a security, whatever the advantage against GI, this gives you that advantage against GI plus 1 is related to that one. And they are related polynomially. So I can only do it polynomially many times, or otherwise I will have the argument that in the end, the final distribution is indistinguishable from completely random. I can only make polynomially many steps in these hybrids to argue that. Actually, sorry, so induction is not like the best tool in these arguments. It's much better to see it explicitly without induction as, okay, here is the series of probabilities, and here is, I have to have polynomially many, each of them is negligible, then I'm convinced that the total size is, you can use this argument in this way, but it's not the most apparent form. I admit that. It's still, I think it's intuitive what was happening. Okay, so what is wrong with this construction though? So the problem is this kind of. So what we are assuming is that we have, let's say that so there is some mysterious algorithms that taken any n bits, if they are random, its outputs are longer, and it somehow mixes in these n random uniform bits in the output so that no one can correlate the outputs. Okay, but clearly the running time of this algorithm will depend on n. It has to look at all the inputs, and if you, for example, try to do it as a circuit, then if you, in hardware, then if you want, this would be some hardware that takes, so let's say the keys are 100 bits. So this is hardware that takes 100 bits, and let's say C is 102, okay? So I take 100 bits, and this circuitry transforms 100 bits into 200. This circuitry transforms 200 into 300. The next one transforms 300 into 400. So you get the drift. This stuff grows and grows. So in terms of circuits, they will look like this. And this whole circuitry will really be what is the dimension here? It's n times I. It's basically P of n, and here it's also P of n. Okay, it just assumes constant is 1. Okay, so otherwise it will scale by C, but that doesn't matter. It's quadratic. So this circuitry, if you look at the area, it's quadratic in the size. Yeah. So this basically, I mean, basically circuitry like this is hopeless, right? You cannot, if I want to output, 1 megabyte, I want to encrypt a megabyte, and like it's a router, so it has to encrypt, megabytes in hardware basically. So now suddenly this hardware has to be of the size megabyte square, which is impossible. Even if you think of software, this is still quadratic. Okay, so if the processing of G is linear in the input size, then this is a quadratic processing here. And it's not clear that you need to do that. So here is an alternative construction, which is linear, and it's also very simple. And somehow, when you see this first one, you're like, well, how can I improve on this, right? Here is an algorithm. So I start with G that takes n bits and outputs n plus c bits, and it's a PRG. I will construct an algorithm G hat I. Okay, so I rounds of G, but I will run these rounds differently. It will do like this. The first thing it will do, it will initialize the state as its input. And then in a loop for I, 1 to I, oh, did I say this? Okay, that's not very good. So let's call it as T. Okay, the I goes from 1 to T. T is the number of rounds. I run G on the previous value of X. So if I is 1, then this is X0, and this will become X1. This will become Z1. How do I parse? This is N bits, and this is C bits. Okay. Okay. Then when I'm done with this loop, I collect all the Z's into one big list. And I will output the last state and the Z. So using this kind of helper algorithm, I will define G without a hat as so run G hat T on X and output just the Z part. And a claim is that for any polynomial P, G P of n is a PRG. Okay, and it's a PRG that maps n bits into I guess C times Pn bits. Okay. Why is this construction better? If you look at this visually, then so X comes in to this. This is G hat construction. I first initialized my state by taking, so this is this is what g hat of t does on x. Okay, it initializes and does the following thing in a loop. It takes its state I minus 1 here and runs a g forward, calls this part of the output xi, and calls this part of the output. So this is n bits and this is c bits, and this is n bits, and calls this part of the output zi, and then recurses. And as he recurses, he spits out z1, z2, z3, concatenates all of them, and this is the right. So the little loop will spit out these EIs and right and create this string as an output. It is better than the previous construction because G runs on a fixed size input every time, right? Rather than take G on the full output, we just cut it at n bits, and we feed only the n bits of output as the input here for the next iteration. So this one has a fixed size hardware. Of course, and okay, so that's great. And in fact, one benefit, what also is implies is that if G goes from say 160 bits to 160 plus C, that's all we need. You only need this standard, this PRG to be well examined, and somehow everybody believing that it has 160-bit security. And that's the only hardware that needs to be implemented. From then on, this construction basically will create for you the PRG that has essentially unlimited range, right? Because anything that is feasible to do, we can model as a polynomial. So, does not matter how long you want to really do it in practice, right? You can do it, yes, as much as you like, basically. Now, you also don't need to know when to stop, because you have this hardware, and let's say that somebody tells you, okay, encrypt 10 megabytes for me. You run it in a circle, you output this as to the point that this has 100 megabytes, you're happy. If this person told me encrypt 200 megabytes, you would run it up to 200 megabytes. You don't need to know what this output, what this limit was. Even better than that, you can run it, and that's why this thing is called stream cipher. You can, so this is the real stream cipher application. The encryption with key K, okay, really has two procedures. Initialize given key K. That procedure sets the initial state as key K. And then it has a procedure encrypt next message block. Where the message block has C bits. And of course, if you want to encrypt more, then you just have to parse them and send encrypt next for each block separately. Okay, so this is without loss of generality. Okay, so what does this do? It computes the next state and the output string as G of X. Oh, so sorry. So actually, I don't need to know. I actually don't need to know my own index, right? So I initialize the state as bit as key k. I run the little g just once on the state, and the left-hand side is my new state. The right-hand side is the string, and I output ciphertext, which is C XOR M. You can also generalize it to T blocks, where this is T blocks of C, and all things that change is just this, and I guess this, right? So I'm now talking about G hat, who runs and keeps track of the state, because that new state is going to be this, and the Z will have enough bits in it to exactly enough to encrypt the message, right? So I actually don't need this because I know how long the message is and how big, right? So I just said for C equal the size of message. No, sorry, for T equal the size of message divided by my block size, right? So I know how long to run because I know how many blocks was in M. And this is how a stream cipher works. You have this little encryptor that really has a state. So this is like an abstract view, but the real view is that he has a little state. This is the state dependent on initial key and number of times E was used. And when a message comes, he's going to output the ciphertext by using this procedure. Right, and the same for decryption. It's just it's the same exact process. Right, like it's the same process because in stream cipher encryption and decryption are basically the same procedure. So of course we are not done with this claim. So far I'm just explaining why this is a good design. Okay, so far so good. So let's argue this claim, right? Like, why is this repeated operation of G in this changed fashion still a PRG?
Professor, just a question. I think you mentioned that the hardware size would be linear on the input, but it's actually like a constant, isn't it?
Yes. Here it's a constant, yes, which is even better, right? So it's a constant, and that's why this is so nice, right? What is linear is the processing time. So if basically when you encrypt a message of basically n is in practice, n is some sort of constant, right? And you have plain text that you are asking, how long would it take me to encrypt a given plain text, right? And it's a linear time because this is obviously the number of rounds is linear in the size of m. Yeah, because it's linear in it's you need to do how many operations is this? Linearity is right here, right? But you're right that the hardware is actually constant sized, or a size of a security parameter. Okay, so so how would we argue this thing? Okay, so let's write what we have. So we assume that G from n bits to n plus c bits is a PRG, and prove that GT that maps n bits into 0, 1, n plus TC bits is a PRG for T, which is P of n for any polynomial P. So Tn is my security parameter, T is the number of rounds, and I say I can run it for as many rounds as anybody would ever want. Okay, because if any feasible computation is polynomial of the security parameter. Okay, and here is the okay. So let's look at these pictorially at what distributions we are here. And you know what? I've never done this, but perhaps okay, this is not very good. Well, okay, let's try. Maybe next time I can use it horizontally and fit more on it, and also zoom a little better. So on the left-hand side, we feed x taken from uniform distribution. We run so no, every time I run a G, I add C bits. So I think, I run it once, I get outputs that are n plus C. Yes, because I actually ignored the good point. Yes, my notation before was this one. Okay, thank you. Okay, now I think it's right. Thanks for pointing out. Okay, so I have this G circuit. I guess let's call this x0, this input, right? So and here it will output x1, and it will also output z1. Then I will pass this to another instance of G, which will output z2 and x2, and so on and so forth. Let's look at the last one. So this is x t minus 1, and it's a G, and here is an xt that I will ignore, and zt here, right? And basically all these form a Z. Okay, And in the extreme case of this, I want to, by claiming that it's a PRG, I want to claim that this distribution coming from here is indistinguishable from just taking a Z uniform in TC. Let's call this distribution D0. And I will call this distribution dt. Why? Because in order to argue that this string and this one, and basically I can implicitly, instead of taking Z like this, I will take Z1 from UC, Z2 from UC, dot, dot, dot. And the last one, ZT, I will also take from UC. And so this will be my Z here. Okay. Somebody is saying something. Is this G hat? No, so I believe this is a G. G hat. G hat is this construction, but also takes care of, basically pays attention to XT. This construction will not. It will just take this output. So I call that a G on my, or GT on this previous slide. Okay, anyway, you see the construction here, right? This is the construction of GT. Okay. Okay. So so now I want to compare these two distributions. The way I will do so is I will consider a hybrid distribution, which I would define DI, which does the following. It takes Z1 at random from UC. It takes Z2 at random, etc., until round I. So I take the first I of these at random. Then I also take from UN, I take XI. And now I repeat the construction. So at that point, so basically I cheat on the first I rounds. Instead of running G, as the construction says, I cheat and take the first ZIs purely at random. At round I stopped cheating. So I run G, and this would give me the Z I plus 1 and X I plus 1, etc., until the last one, which gives me ZT and the states that I ignore. And this thing will, of course, be my Z. And I'll call this distribution DI. So basically, you know, there's a break here. All of these are purely random. These are outputs. I can see them as outputs of G. How many rounds of G I took? I basically skipped the first I rounds. So I think this is T minus I applied to Xi. So this Z is the compound. The first IC bits are purely random. The last T minus I C bits are outputs of a round reduced. So this is can be called a round reduced G, right? GT. So instead of going full T rounds, I skipped a few first ones. So that is what DI is. So DI is basically outputs is what? Z let's call it like this, concatenated with G T minus 1 T minus I of Xi, where Zi was uniform IC bits and Xi was a uniform N bits. Hybrid distribution is a good word because what is D0? So I actually stalled you, but let's work this out. What is D0? D0 is I with this with I0. So basically this is empty. There is no Z0 hat is a Z0 bar is an empty string, right? Because you're taking 0 bits. But you take X0 at random and you run, this is empty, G of T on X0. Well, that's exactly, this is just outputs of GT on X for X uniform. So it's correct. What's DT, the other end of the spectrum? Well, what is G to T minus T? It's G to the 0. It's like I don't do G at all. It's round reduced extremely, as in there is no rounds. Okay, right? Like this guy doesn't do anything. So this doesn't output anything. Everything is in here. And this is how many bits? TC bits, which is what I needed, right? So GT is a uniform TC bits, which is this. But it's a hybrid because G0 and GT are the distributions I should consider asking whether this is a PRG, right? Whether or not GT is a PRG is to say, is this distribution indistinguishable? I'm creating these guys as helpers in this argument. They are going to be helpers like this. Let Pi be the probability that A on Z outputs 1, given that Z comes from distribution Di. So advantage of A in attacking this in attacking the PRG, right, is basically the distance between P0 and PT. This P0 is the probability of what attacker says on this distribution, outputs of GT. PT is the probability that he outputs 1 on uniform string. So the advantage is difference between P0 and PT. But here is the triangle inequality. If that there must exist some index such that the difference between Pi and Pi plus 1 is at least the difference between P0 and Pt divided by T. If he acts with the probability P0 here and the probability, and you draw them on the line, then no matter how you place these PIs, and we don't know, we cannot assume anything about how attacker acts when he gets these hybrid distributions. Perhaps he throws up his hands and he says, these distributions are, I'm refusing to output anything on them, right? Still, does not matter. There's some probability with which he outputs 1. Maybe it's 0, but it is some integer. Well, the worst case is like if they are spread out like this, but it cannot be that this distance between, for every I, is less than the total distance divided by the number of these steps. It must be that at least at some point you're making a step that is what you need to walk throughout divided by the number of steps, right? You cannot get from this point to this point in T steps unless one of the steps is greater or equal to this quantity. So that means that if advantage of A against PRG is greater or equal to epsilon and it's not negligible, so in other words, by contradiction, by counterpositive, assume A breaks GT, right? So assume there exists some attacker that distinguishes between these two distributions, call it A. He has advantage whatever P0 minus PT is. Let's call it epsilon. And it's not negligible. Then there exists an I such that Pi minus Pi plus 1 is at least epsilon over T. And this is also not negligible, right? Because T is polynomial, right? So if you divide not negligible by polynomial, you still get not negligible. Right, sort of obverse of the homework exercises, right? Because, you know, if the result of the division was negligible, then it wouldn't be the case that you show on the homework that if you take negligible and you multiply by the polynomial, you have to get negligible back, right? And here you assume that you started with a non-negligible. So let's look at the difference between what does it, you know, what does it mean that you have this attacker and he does distinguish between these two, but by the beauty of this hybrid distribution, you have also pinpointed not only he distinguishes these two with non-negligible advantage, he also, there must exist a step here, call it I, such that he distinguishes di from di plus 1 with non-negligible probability. And the whole exercise is because at that place, when we see what a di is and what a di plus 1 is, then we will reduce to the security of this PRG. Okay, so let's look at what the di plus 1 is. Okay. What is di plus 1 according to the same procedure? Okay. So from UC, I take Z1. From UC, I take Z2, dot, dot, dot. From UC, I take ZI, and I go one more step in my cheating, right? So these are the first I+1 rounds now are skipped. So now these are all random, and so is this one. And that's the difference between these two. Okay, let's see what happens next. The next is that from UN, I take X I+1, and I feed it into the G, which will generate Z I+2, and da 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 da. So the rest is a G, ZT at the end. Okay, and now this whole thing is my Z, and that's the distribution. So I take the first I+1 at random, and I run the round reduced. Okay, so this round reduced took T minus I rounds. I wish I left myself more space. This round reduced will take one less round, right? So it's T minus I minus 1 of G of X I plus 1. Now, let me do one more change here. I will feed it to G explicitly and show, and show one more step of this guy, and here dot dot dot. Let me see if I have a different color. I should have prepared a different color thing, maybe with a pencil. This part, this block of computation, actually I should have drawn it differently. This block of computation, sorry, and this one are identical. So in this, I picked these ZIs, then I picked XI, it created XI plus 1 and ZI plus 1. What I did with X plus 1, I plus 1, I put it into this circuitry. What I did here, I picked ZI plus 1, I chose XI plus 1, and I put it in this circuitry. These two circuits are identical, right? I mean, it outputs this useless state. You know what? Let's erase it, because it seems like I'm not using it at all. Okay. So these two circuits are identical. What else is identical between them? This process, the way I chose the first I, this is also identical, right? So these two are the same, and these two are the same. So the only difference between the way DI is built, so what is DI? It's a result of an algorithm, a randomized algorithm. The randomized algorithm picks the first I at random, then picks a seed and runs round reduced G, reduced by I rounds. That's the way DI is built. The way DI plus 1 is built, pick first I plus 1 things at random, pick a seed and run round reduced G on that seed, reduced by one more round. Hold on, T minus I -1. Yes, so I subtracted one more round, right, from GT. And these two processes have a lot of circuitry in common. The only different one is this. Here, so what differs these two processes is, I wish, hold on, I should have prepared a colorful thing. Hold on. Of course, when I need it, I don't have it. I cannot find it. I guess, is this pink? Maybe it is. Yes, it is. Okay, good. Focus on these two. How are they created here versus how are they created here? And this process runs this circuit to get these. It's the same circuit generates these. Then some processes generates the red pair here, and some other process generates the red pair here. Note, this process is independent of this circuitry. It's basically done its job and can go away now. I pick this pair differently than here. But once I do so, the rest of the process is identical again. So I pick this pair this way here, this way there, but after that the difference vanished. I took whatever xi+1 was and ran this circuit. I take whatever xi+1 is and run the same circuit. So that's where my reduction to PRG security lies, because the only difference in how these two guys came about versus how these came about is that on the left-hand side, these two guys are an output of a G on a random seed. Whereas in the right-hand side, these two guys are a random string, because I took UN and UC for this. So this came from a random n plus c bits. So my conclusion is that DI and DI+1 are both results of some process R. I chose this name judiciously. It would stand for reduction on input, which is xi+1, comma zi+1. It's this red string. The reduction does what? The reduction on this input picks z1 to zi all at random. So this came from IC bits. And it picks zi+2 ZT as an output of round reduced G T minus I minus 1 of what? This part, X I+1. And that's it. And, and outputs the obvious thing, which is the concatenation of all the Z's, right? And are both results of some process on some the DI is the same as to run R on xi+1 zi plus 1 were such that xi plus 1, zi plus 1 are outputs of G on xi for random xi. Di plus 1 is the same as R on xi plus 1, zi plus 1 for such that this xi plus 1, zi plus 1 came from random u n plus c bits, right? The first thing is random, and the second random n bits here, random c bits here. So I don't have space, but the conclusion is that this is R is an explicit reduction. That okay, R is a okay. Now I'm really in trouble. I don't have space. Let's see how this works. Okay. Better. It's probably hard to read, right? Do you guys see these marks I'm making? I mean, can you see that this is x I plus 1 and z I plus 1, etc.? I don't know if it's possible to see on a Zoom. Do you guys see that or no? Not very clear. So I see. Yeah. What I can do is, yes, so basically I have to use horizontal. I will use horizontal like this, and then I can show more. Yeah, I should have done that. Is this a resolution at which you actually see the stuff clearly? Oh, okay. Okay, sorry. So sorry about that. So yeah. Okay, I guess you didn't know that I can do that, and I didn't know that I should have done that. Sorry, some miscommunication there. Okay, hopefully when I zoomed, everybody was like, "Oh yes, I thought that that's what it's supposed to be." But yeah, sorry about that. So okay, so what do we have here again? So di is the result. So R is the process that takes the red string, whatever it is, and generates, picks these at random and picks these guys as a round reduced G applied to the left part. And this reduction starts with a red string. And if the red string came from this distribution, random outputs of G on some uniform seed, then the reduction will generate this view. So it will hit di. But if the input string came from this distribution, then the reduction would regenerate di plus 1. So the conclusion is that if A is a difference, you know, the reduction will generate this Z and feed it to this attacker A, right? Because we assumed that attacker has a decent chance epsilon between these two, and therefore by triangle inequality that it has a decent enough epsilon over polynomial, so therefore still not negligible chance of distinction between these two. So if reduction feeds the Z that it creates to attacker and outputs a bit, it will have exactly this advantage over the underlying PRG, right? Right, because the reduction will be faced with a red string either generated by a PRG or generated at random. And it will have this distribution, this advantage on it. Okay, maybe I take questions at this point. I mean, so speak up, because I'm sorry that it was blurred before.
Hello, Professor. I have a question.
Mm-hmm.
So for this triangle inequality line, so we're basically I can think of as the P0 minus PT. That difference is basically a sum of each individual step, Pi minus Pi plus 1, right?
Right.
Then you can do the triangle inequality. Why is it the case that P0 minus PT is the sum of each individual step?
Well, it's not exactly a sum, right? It's just upper bounded by 1. So P0 minus Pn is well, it's a difference between P0 minus P1 plus P1 minus P2 plus ... right? Pi minus Pi plus 1 plus the last one, Pn minus 1 minus Pn. Right? So far so good, because this cancels, each of them cancel except of the last ones. So I have this.
Oh, I see.
So now, if it is the case that each of them is smaller, if for all I, Pi minus Pi plus 1 is smaller than epsilon, okay, than epsilon over n, then the difference between these two, right, must be smaller than epsilon.
I see.
Right, because each of them is. So if the absolute value is, then so is the value without absolute value, right? It's also smaller than epsilon over n. So conversely, if P0 minus P1 is equal to epsilon, then this part cannot be true, and therefore there exists an I such that Pi minus Pi plus 1 is at least epsilon n, right? I'm just contradicting this part. And that's exactly what we wrote here, right? That there exists an I that is at least total distance minus the number of steps.
I see. Yeah. Okay. Thank you.
Welcome. Okay. So this also explains why I consider this hybrid, right? So the hybrid was precisely done so that I have a smooth transitions here, and intuitively the difference between total application of GT and purely random string is that here I have T applications of G on the left-hand side, right? And how can I argue about that if somebody runs T G instances in some complicated fashion, although not that complicated, but still, and if attacker distinguishes the string from that, then I can distinguish a single output of G from a random. You cannot argue this really. You know, there would be no reduction that directly takes either either some string that is purely random or some string that is an output of a PRG, and somehow embeds that string directly into this or this. And if that string is purely random, reduction hits here. And if that string was an output of a PRG, the reduction hits here. Because just think like, okay, how many times R runs G? If it doesn't run it at all, then I guess it can hit here, but it will never hit here because this guy runs G T times. So you just, I mean, no one can think of this type of reduction that directly embeds the view. But once you modify it in this hybrid way, where basically you consider round reduced versions reduced by one more application, so one more G instance drops out as I move from left to right, then at each step, they differ only in one application of G. And now I can have a reduction. The fact that it's only one application of G that differs them does not guarantee the reduction. What guarantees the reduction is that the whole construction can be viewed, or rather this hybrid cheating way can be viewed as two independent processes that in a black box way start with either an output of G or a purely random string, and the rest is independent. So for example, none of the stuff re-enters here. None of this stuff re-enters here. If I try to complicate this reduction, right, and let's say I take these bits and somehow feed them, right, if I try to make it quote unquote more secure by doing some other operations between them, then this more security would translate into inability to prove anything. And sometimes actually this type of introducing correlations like this actually does not make it more secure. The fact that you cannot prove it is very, very good reasons you cannot prove it, because you destroyed security, because you actually created correlations which are detrimental, and which would, it would no longer be the case that you start with the PRG and you have a secure construction. So you created the security vulnerability rather than an improvement. And this basic thing appears again and again. People try to make stuff that looks more secure by making it more complicated. Now, first of all, they mess up any reasonable security argument. And then, you know, it's a gray area, so you cannot argue, but is it insecure? Well, often enough, it's not provable because it's insecure, because these extra correlations don't help. So you will see this, that as you create a cryptographic construction like this one, there is sort of at least two aims. One is for this to be efficient, right? To generate the string in some way that is not too arduous. But second, of course, that it's secure. And that part basically means that there has to be a proof. There has to be proof by reduction, because, you know, there's clearly no hope of creating this kind of big PRG without assuming that the internal little PRG is secure. The best you can hope for is that this big PRG is as secure as the small PRG, right? That the inner circuit here that goes in the loop, basically, so in the real world, this is the inner loop that goes, right, the inner circuit that goes in a loop. We assume that this inner circuit is a PRG then the whole thing will be. Okay. Now, clearly, I didn't say, still, where do we get this little guy, right? So we have to start from something. What this tells you is that the minute I have something, I have n+1. Even if I had n+1, I could run this. It would not be the best, because if the little circuitry just gives me 1 bit, if I want to get 1,000 bits, I have to run 1,000 times. If each of these gives me 100 bits natively, I have to just run 10. Of course, this latter is better. But who knows what's inside circuitry here? Maybe it's a tiny PRG that extends just 1 bit executed 100 times as a copy of this construction, right? So that could very well be. But the question still is, how do we get even this initial single bit? Okay, and we haven't answered it. What we answered is that the moment you have tiny PRGs that even gets you 1 more bit here, that's enough. You can now run it in a loop and get as many bits as you please. So of course we'll revisit this issue, where this little guy came from, but we'll do it, step by step. Okay, so I'll copy these, and hopefully the JPEG gets a better resolution than a video, and I will post them as well. Tell me if you have any questions. All right, so I'll see you on Wednesday. I saw there's office hours tomorrow at 2, if you want to talk. Okay, take care, everyone.